Excel, and I think that will be the time of your last meeting.
Okay.
So we can quickly touch
That's
base.
great.
And
That's
then
great.
we see each other at 6:30 again.
All right,
Okay.
cool. Thank you. So we're attempting to record the seminar right now. We're waiting for somebody to start the recording. That's why we're a few minutes behind schedule. Hopefully they'll be here in a few minutes.
Is this the first seminar that will be recorded?
It is. And depending on how successful it is, we'll make a habit.
Are we going to be in the recording or?
I don't know where you're going with this, but I would suggest that everybody behaves because everything will be recorded and posted. I think the audience will not be in the cameras.
They can't hear your terrible questions, is what he's trying to say.
Or yours, right?
We could get a microphone and so that they're hiding in the closet.
Okay, we'll give them 2 more minutes. Linda went to look for them. I don't quite know if she's finding them. Sorry about that.
That's fine, good. Why you guys want to start recording?
Because we have a lot of great speakers. We thought,
okay.
forget all the talks.
Okay, I see.
I think it's time to move to the 21st century.
That's right.
We'll probably have to give you slides as well.
Sure, no problem. Yeah, that'd be great. Yeah. That's good, yeah.
Linda did not do it yet, right? We have not streamlined this very well yet.
Okay, I see. Hey, yes.
So when you mention voice use, do you always put the in front of it?
That's the official name.
Yeah, because in the logo I can see it's.
Yeah, as well. Yeah, I won't.
It's
I
still
yeah.
called OSU, right? It's still.
Yeah, people make fun of it, so this. I prefer not to. Was it start? Uh-huh.
After we start, so we can go and check where they are because we need that one to look for them.
Okay.
But I'll get you started to make sure we're not.
Okay.
Okay, so we're going to start, and we'll be doing some soon. So it's a pleasure to start the seminar series this year with Professor Wei Zhang from The Ohio State University, or DOSU.
So I see
Professor
here.
Zhang first got his PhD in 2009 at Purdue, and after a brief stint at Berkeley as a postdoc, he started at The Ohio State University.
Mm-hmm.
His research interests are in power system, robotics, game theory, and hybrid systems, and he's received several awards for his research, notably the NSF Career Award in 2016, so the last batch of the Career Award, and also the Lumley Research Award from the College of Engineering at OSU. So his talk today is titled Game Theoretic Approaches for Complex Cyber-Physical Systems. So the floor is yours.
Okay. Thanks for the introduction. Thanks everyone for coming. It's my great pleasure to come here to speak about my research. And again, my name is Wei. In general speaking, my research focuses on control theory and applications, just similar to most of you. For the theoretical part, my focus is mainly on hybrid systems. Has been mainly on hybrid systems since I was a PhD student. But recently, I got interested in games, so that will be the topic for today. Okay. So I'm going to speak about different type of games today, and for different applications that I've been working on before. And the first one is about differential zero-sum games for motion planning of robotic systems. And the second part is more about mean field games. And I have been talking to a few faculty members here. I feel like it's more interested in the mean field game part, so I'll be relatively short in the first part and make sure I have enough time for the second part. Okay. So when we start this problem, our motivation is that we feel like human actually can do many extraordinary things that robot cannot really do, at least for now or in the near future. But on the other hand, we realize robot automation is much better than human in computation or many kind of decision-making tasks. And our goal is that a question we're trying to ask is that how can we construct or design a human automation team that can combine the strengths of human and automation to accomplish tasks that are impossible for either human or automation itself. Okay, that's our initial big picture. Well, this is very ambitious. To make this ambitious goal concrete, we start developing a so-called capture flag testbed. I'm not sure how many of you have played with or heard about the capture flag game. Already? Okay, well, I never played this game before. But we have a Chinese version of similar games, I think. So basically, there's a popular outdoor games that you have two teams of agents. Each team has a flag. In order to one side of team to win the game, you need to bring the other side of the team and bring it back to the home area or return area. During the whole process, you cannot be tagged by your opponents. That's the rules of there are different variations, but that's roughly the rules of this game. Okay. So the idea of our test bed. That was maybe 7 years ago when I was still at Berkeley. The test bed was that we want to use the UAV in our lab to sense the player locations. And we want to send this location to the server. And in the server, we want to have some kind of nowadays you may call AI algorithms, right? To compute some moment recommendation for the human players through the smartphone. Okay. We envision this kind of test bed will be a rich kind of a platform to study many kind of human automation collaborative decisions. Okay, so that's our initial idea for constructing this test bed. But the problem is that in order for this type of test bed to work, the first question we need to answer is that what's the optimal solution to this game, right? So what kind of movement recommendation need to send to the players? Okay, so to answer this question, we need some kind of mathematical formulation of the capture flag game that has not been done. We feel like at that time was not done in the literature. Okay. So it's pretty natural, okay, to think about this in the differential game or zero-sum games, right? Suppose we have an OK model to describe the player's motion. Let's say it's a dynamical system, each player, right? And suppose we can measure or have a good estimate of the player locations, right? Then this is nothing but a differential game between two competing teams, right? So by solving the solution of the game, we mean that we need to determine the winning region, which is the set of initial states of all the players starting from where one side of the team can guarantee to win the game, regardless of the other side, what the other side is doing. Okay? And we also want to find the corresponding winning strategy can lead to this victory. That's the solution we mean, all right? So this game is very similar to the classical pursuit evasion game, right? But it's a little bit more complicated than a plain pursuit evasion game because it has multiple objectives. You're not just running away from each other. It's just while you're running away, you're trying to get the flag while trying to escape or avoid being captured, right? And also there are multiple stages. The strategy you apply before you capture flag, after you capture flag should be different. Okay, so it's a little bit more complicated than that. And so in that sense, we focus on just a newer part of this game, newer feature of this game is focus on two-player capture the flag game. And even for that, okay, different game formulation is easy to set up conceptually, but a lot of different details you need to worry about. For example, what running costs, what terminal costs, and what kind of solution you want to provide to the human players. So we want a way to solve the problem that can facilitate interaction with humans so that they can easily incorporate this recommendation into their decision making. So that's what's the guideline. It turns out to solve this problem, for this reason, we adopt the so-called reachability calculation approach. It turns out the basic building block for solving this problem is the so-called reach avoid set calculation. Let me just briefly get into this. All right. So let's consider a general dynamical system. Okay, continuous time. This is your U. This is disturbance or the material input. Okay, there are constraints as well. So the reach avoid set is nothing but the initial state of the system, starting from where there is guaranteed to have a control that can drive you to the goal region during the whole process without hitting the void region. The set consists of all these kind of states. All right. So long story short, the key result, or classical result in this field, that's been done a long time ago, is that this reach avoid set, if you give me this dynamical system, give me the goal region and the void region, I can compute and characterize this reach avoid set by solving related Hamilton-Jacobi equation. Okay, and the set is characterized by the sub-zero level, sub-zero sub-level set of the value function of this, the value function that which is the solution to this HJI equation. Okay, I don't want to get into details of this. This is not new. So the key part is that we can remember now is that if you gave me the goal set, avoid set, and dynamical system, somehow let's believe we can solve at least in this certain low dimension, we can solve this reach avoid set. Okay. Let's treat this as a MATLAB function now. Right? So let's see how this thing can help us find the solution of the capture flag game. Okay, for capture flag game, let's start with, so we need to consider the problem in the joint configuration space. This is the attacker's location. This is the defender's location, right? So let's first consider the case, second stage of the game. So the attacker already got the flag, all right? So in order for him to win, the winning reason is that all the locations in the joint configuration space for which the attacker can safely bring the flag back to the home return region. Okay? In the language of reach avoid, it's nothing but you want to reach the return region while avoid the capture region in the joint space, and also without going out of this game domain. This is the complement of the game domain. This is reach avoid computation for the second state of game, right? However, if you haven't got the flag, you need to consider two states of the game. It's just very simple as well. You need to first reach the flag region without being captured, right? But it's not all the part of the flag region is helpful. You only want to reach the part of the flag region, this is the flag region, the part of flag region in the joint configuration space from where you can safely return. You can win the second stage, right? So it's a nested kind of reach avoid computation, right? So you find the second state, then you do another reach avoid computation. That's roughly the idea. Okay? But you may ask, okay, how do we solve this? Okay, at least in low-dimensional case, in simple dynamic, let's say, dynamic can be a little bit more complicated than this. The state dimension is the main key. Okay, let's say we can use the level set toolbox to find. Okay, in this particular case, for example, Suppose this is my attacker location, right? I'm drawing from the defender's perspective now, okay, because I can only show 2D, right? So this part, RD, is all the defender location from where he can stop the attacker from return. Okay, he can win the second state of game. And this part, FD, is part of defender location from where he can prevent the attacker from capture the flag. Okay, that's the solved using this level set 2 box. And but this whole thing, the overall winning reason is WD. Okay, it's much bigger than the union of these two. For example, if you are here, that means you cannot prevent attacker from capture flag, but you can still win the game by better prepare yourself for winning the second stage of the game, right? The key is that our intuition is that, so this set, even for these very simple dynamic models, those sets are non-trivial shapes, okay? It's hard for human player to figure out those things, right? It's good for the computer to show those things to the human, and that they can better incorporate this into their decision-making process. Okay, so here's some kind of animation on that. So basically, so suppose this is the attacker, this is the defender, this is outside the overall winning reason, so he cannot really stop, he cannot win the game. So this is basically the equilibrium solution, by the way. Okay, and in this case, the defender is inside the winning region, but it's outside the winning region of the capture the first stage. That means he cannot stop him from capture the flag. So he directly gave up, because the optimal solution, he gave up the first stage directly, but positioned himself to be a location that he can win this, guaranteed to win the second stage of the game. So we ran a little bit similar experiments before, and that was a long time ago. Still, they can only walk. And this experiment means that this guy starts inside the winning region. This is the attacker. But he has a phone. Sorry, okay, so he has the phone, and he can better make decisions. So initially, the defender is inside his winning region, but he wasn't able to win the game. Okay, the point is that with this decision support, the defender can win the game, even though he was not supposed to do that if everyone play optimally. All right. So that's the result we have for that capture flag game. Okay, the main bottleneck, I think the main bottleneck is the following: is how to generalize these to multiple player games, right? That's the part, it's the curve dimensionality. For that, we do a little bit extension, and we look even the more simple case, just the pursuit evasion case. In this case, suppose I have a bounded domain, I have multiple pursuers, one evaders. Okay, the optimal solution in this case is hard to find, okay? But there's still some ways you can try to capture it. For example, a direct shooting at the evader, that's some simple strategy, but this strategy you feel like there's no cooperation among the pursuers, right? And it keeps forever and to capture the evader, and there's almost no cooperation between them, okay? But we know that optimal strategy is impossible, okay? The question we're asking now is that, okay, can we find something in between, in the sense that better than this kind of simple pursuit, more cooperation, but also we want to make sure we can guarantee capture eventually. Okay, so guarantee capture is not hard once you have a bounded domain. But we just don't want to lose that kind of a guarantee. If you design some fancy algorithm, you may lose some even simple guarantees. All right, so that was the motivation at that time, and we proposed a particular way that called Verdonov-based partition-based pursuit. The rough idea is the following, that I have multiple pursuers, and the pursuer strategy is nothing but jointly minimize the area of the Verdonov partition of the evader. Okay? Why this is good? It's almost like intuitive, almost like you're trying to limit the future possible location the evader can be. All right? And the good thing is that we have another form of this strategy that you can compute offline. Very easily computed. And also there's a very nice cooperative behavior that can be induced by this strategy. Okay. And also we prove that it also guarantee capture even with one pursuer in this case. If you look at the same example, now you have 3 pursuers. These 3 pursuers actually started even further away than this one. But this guy, the left-hand side, you use a simple pursuit. This one is trying to do this based partition gaze. You can see the pursuer trying to cooperate right, encircle this evader, and eventually corner him, and there's nowhere to go, he will be captured. Okay, it's more like a cooperation better, and to capture it. So that's some kind of a heuristic idea, but we have a capture guarantee as well. So we also do some field experiment as well, but I want to show something else, which is happening in real AI computation. So this is what happened in the real AI computation. So it was discovered by the enemy. Everything is played by computer. Okay, so you can see there's a lot of pursuit evasion problem here. Okay, so it was not well designed AI. And let me see. So okay, so in this case we implement my collaborator implement this in this game, and we're not based partisan game and pursuit strategy. So in this case, you can see the drones are trying to run away from the Zerglings, and the Zergling trying to encircle it, right? And it's more cooperation in this case, all right? So that's just a nice way to show this is intuitive idea works. Okay, and as I mentioned, I want to speed up this part so that I have more time for the second part. So I wouldn't talk too much about this extension in the non-convex domain. Roughly speaking, this idea can be extended to non-convex domain, but vernal partition doesn't immediately extend to this case. Right? I mean, if you have nonlinear domain and also heterogeneous agent with different speed, and this doesn't work. And we find a particular way to generalize the vernal partition, which is called safe reachable set. Okay, and in the convex domain, this safe reachable set will be the vernal partition, but in non-convex case, it just consists of all the points the evader can go without being captured in the open loop sense. Okay, I wouldn't go into details, but this in non-convex case, you need to solve a partial differential equation in this case, but the complexity only grow linearly as the number of agent increase, only pairwise computation. Okay, this is the example that's for non-convex domain, different speed. These are these safe reachable set based cooperative pursuit. All right. So, so let's quickly conclude the first part. We feel like game theory is useful for different type of applications. One particular application is the security or safety based decision making for under adversarial uncertainties. This is one example here. And in particular, the take-home method I would say is that reservoir set computation is kind of a modular way to solve a more complex differential game. Sometimes it's pretty helpful. And if you have multiple pursuer case, and the vernal-based partition is one nice way to encourage cooperation between among different pursuers. Okay, so if you're interested, you can find into our papers on this topic. Okay, so let's yes, sir.
What's the intuition behind this algorithm for minimizing the area where I sell?
It's intuition is just it's intuitively those are the places there you have no control. You cannot capture them.
Right, but I'm asking what is the actual algorithm? Like how do you intuitively explain
The algorithm.
how the algorithm works?
The vernal partition in convex domain, you can compute this area analytically. And you want to minimize the area with respect to each pursuer's location. In that case, you have analytical form of the control law. Yeah, I do have analytical control law in that case. But in non-convex case, everything is stored as a strategy because you can compute offline. Okay, so but that's yes. Any other questions, by the way? Okay, so let's switch gear and to the second part of the talk, which is mean field games. All right, and actually, when I started working on this problem, I was not intended to work on mean field game theory, let's say. I had a particular problem at hand, application problem I need to solve. Later on, I find out there's no existing tools, somehow, at least we didn't find tools that we can directly use to solve our problem. So we work on a little bit of the theoretical part. We're relatively new on this topic, so try to get your feedbacks, okay? So let me give you some background where I started this problem, okay? As I mentioned, I'm not starting from pure theoretical application. The things motivate me is the so-called cyber-physical social system. It's a very broad term. What I mean by that is anything like demand response. You have a large number of loads. Intelligent transportation systems, you need to coordinate different vehicles, or smart parking, or cloud computing even. What's the commonality among those things? Well, those systems all consist of a large population of agents. Okay, these agents typically have decoupled dynamics, right? Their physical evolution does not immediately depend on each other, but they are coupled due to shared environment or resources. So the coupling are typically on the cost function or some constraints, right? So, and another feature of those problems is that the coupling is typically weak in the sense that it's only depend on the aggregate effect instead of individual behaviors. So how much, which road I need to take my decision making doesn't depend on whether agent A takes a particular path or not. It really depends on how many total number of vehicles on each segment along my path. All right, that's the aggregate effect. Okay, another thing is that, well, because they share environmental resources, we need coordination, right? And the typical way to formulate problem is optimization, right? You say, I do about optimization. However, in this case, in this kind of system, it's often not feasible to do that because human will be a key part of the decision-making process, okay? And you cannot directly say this load, you need to consume a certain amount of energy over this period of time, or you have to take this road. That's not going to happen. Even fully autonomous vehicle, you are serving some passenger inside. You just have no driver, right, typically. You still need to serve someone. You have to respect the preferences and of if you don't do that, you may know that you will run into something like a Brass paradox, right? The social planner want to build the actual road to reduce the delay, but the strategic behavior among agents will actually increase the delay, although you have more resources in this case. Okay. For a more recent example is the Uber. Okay, the pricing was not done perfectly, so that these some of Uber drivers, they will simultaneously log off from the system. Okay, and when their search price, they come back. They start gaming the system. So what I mean by that is you have to, the social planner, when they try to design the coordination system for this problem, they have to anticipate the potential strategic interactions among human players. Okay, so this brings us to the two basic questions, research questions. One is that how do we analyze, right, or analysis? How do we model the emerging interaction among strategic decision makers in this case? And this will be a modeling analysis. And second one is how do we design, right? If the equilibrium is not good, how do we design a mechanism or strategy that encourages good equilibrium? That's the more challenging problem. But both problems involve games, all right? And you may ask, okay, that's not new. Okay, games have been done for many, many, many years, right? And here, you're familiar with games. And so games actually has been used a lot in engineering applications. Here we have some kind of problem I mentioned. They have some emerging challenges. Typically, you have a pretty large number of them. You don't have just one or two, right? You have a large number of them. And also, oftentimes, these agents are not static, typically have dynamic behaviors, in the sense that the amount of energy I consume during this period of time will affect the energy I need to consume in the next period of time. There's some coupling about my decision making that make the system overall complicated. Okay, analysis of a large-scale dynamic game is except for some special cases, right? One of the most well-known special games that you can reasonably do well is the so-called pretend game, right? So in pretend game is fine. You have a net equilibrium, and the batch response always converge. There's many nice properties. And I will argue another important class of games that you can simplify, or there's a hope that you can solve the problem, is the mean field game. Okay, and how do they relate it? Do they really relate to each other? Not directly. All right, I will feel that there are different class of games, but there do exist some cases that are both potential game and mean field games. Okay, I don't think people in the literature have studied this part, but I will mainly focus on mean field game for this rest of the topic because of my application. But at the end, I will talk about this intersection point cases. So I'm not sure how many. I mean, I will just try to I try to make sure everyone on the same page. I will give a brief overview on these mean field games. Some of you may know this already. Okay. The typical setup of mean field games is the following. Agents are typically described by a dynamical system. Let's say agent 1, I, or N. They are subject to dynamic system will have state and control. I'm not to be very precise, just want to highlight the main idea. Okay. And so their cost functions, typically their cost functions or dynamics depend on other agent states. Okay, so their decisions are coupled. Everyone depends on everyone else. Okay. And in general, this game is almost impossible to solve in general, right? And one particular structure of the mean field game is that the coupling is weak in the sense that only depend on some aggregate information, for example, the sum or average value of other agent states. Or in this case, I'm writing this is the empirical distribution of the population. Okay? So because of this structure, I can leverage this to simplify the game a lot. Because if I call this coupling term, this aggregate term like a mass term, okay? If I call this term fixed and that's given, then the decision becomes fully decoupled. At least on this layer is fully decoupled. Okay? If these mass terms are fixed and given externally, then this agent doesn't need to worry about each other. They are fully decoupled. However, of course, that's easy because the coupling now is between the mass term now. If you make your decision, will affect my mass term here, right? So there's still some coupling here. But it's easy to see that those couplings are going to be getting smaller and smaller as the number of agents increase, right? Okay, in the limit, the hope is that all these mass terms will not be affected by any single movement of these agents. So I will have the same mass term. Okay, so that's why people typically in the mean field game literature, they will study this, instead of study this finite agent case where the real problem lies, they will study the so-called continuum agent model. Okay, in this case, the mass term, the ensemble distribution or empirical distribution will become a density function of the state, right? And then agent dynamics not only depends on the mass term, it depends on the density function. Okay, so given this density function, I can solve an optimal control based on the continuum model, dynamic model, to find optimal control law. Okay, and if you plug in this optimal control law, and it will affect the density evolution, that's the forward equation. Okay, and the fixed point of this loop will give you the mean field equations. It's a very rough idea, right? So the fixed point of this. And why people study this, I mean, they all study this case, okay, by the way, the continuum model, most of them. Why this is they study this? Because the solution of this really give you insight about this finite game that you were initially started with, right? So that means the main result is that if you plug in this control law, you compute it through this fixed point solution, the mean field equations, and you apply this, and you have this, you plug in this density function, you compute it from this one, you get a set of decisions, and these strategies are epsilon naught for these finite games. What I mean by epsilon naught? So it's just epsilon naught means that unilateral deviation from this equilibrium can only reduce the cost by, at most, let's say, epsilon. And the point here is that this epsilon goes to 0 as n goes to infinity. Okay, more or less the mean field literature is all about this. Okay, it's a different ways to say the same idea. Okay, given the mean, compute the optimal control law. Given the optimal control law, you need to generate the same kind of distribution. All right, it's all a different way to state the same idea under different assumptions, different models. Okay, so if you look at literature, okay, typically how do they describe agent models? They use stochastic differential equation. Okay, I don't know why stochastic differential was preferred, but this is the case in the literature. It's a little bit more technical. And given this by this Fokker-Planck equation that's well known. Because that's the evolution governed by forward equation, which is the Fokker-Planck equation. Okay, so they need to solve these coupled PDEs. Most of the mean field theory is trying to study uniqueness or existent uniqueness result and under this FDE model and also additional assumptions. Okay, a lot of assumptions typically, very technical, I'll say. Okay, so what I feel that existent uniqueness may not be enough. Result discussing how to compute or solve this mean field equilibrium. Okay, just very, very little, I would say. No general theory on that. And more importantly, those are mostly about describing the equilibrium of a game. It's just modeling or characterization of the game, right? So what happened is this equilibrium is good or bad, there's no comments, right? So very few tools can tell you how to design mean field game accomplish also Planner's objective. Okay, so these are also the things we are not happy with mean field game theory. Okay, so let's give you some example, concrete examples. Okay, let's start with this almost one of the most famous examples by Ma and Ian Hiskins and Duncan Collins. It's a PV charging application, one of the most successful applications on mean field. Okay, very simple game, by the way, in this case, no FDE. So suppose we have a coordinator that need to coordinate charging within the region through real-time pressing. Okay, so in this case, each vehicle dynamics is just simple as state of charge dynamics. At the end, you need to reach some desired SOC. Okay, and their objective is just trying to minimize, individual need to minimize the energy consumption, or sorry, energy cost. Right, energy cost at any given period of time is the energy you consume during this period of time times the price. As simple as that, right? But because of this price function, real-time pricing depends on the real-time actual energy, total energy consumption, depends on the sum of all the agents, possibly plus some other uncontrollable part as well. But anyway, so this pricing function actually couples everyone's decision, right? In this case, you will have a game. Okay? And they argue also this game is hard to solve, but you can. This is a mean field game. Propose a solution to solve this problem. And they find out, okay, the mean field equilibrium has some kind of eddy feeding property. Most people will charge overnight in that case. Okay. So I have two comments here. One is that derivation of this mean field equation is following similar idea or almost the same idea as the mean field literature. But they cannot directly use the Hamilton-Jacobi whatever mean field equation here because the model are different. Second is that this is still a mean field equilibrium analysis. Okay, so what happens if I don't want this value here? Just tell me this is the game and this is the result. What happens from social planner perspective? If I want something, I hope you can design a game so that the emerging figure of the population accomplishes my objective. Right? So this part, I think there's not much tool that can help us address these issues. If you look at other papers, in the literature, there's a lot of applications. Most of them basically does two things. Describe an application as a mean field game and derive mean field equations. And that's almost the end. Most of them stopped. Some of them may propose some algorithm, but in general, their algorithm even doesn't really. Some of them mention explicitly, okay, we don't know how to formally compute the mean field. It's not as lucky as the previous. The previous one is already the most successful application. I also want to point out some of you may be more familiar with other type of applications in field games. For example, congestion games. I think everyone studied game theory. Almost the first, the most important example is the congestion game. Congestion game, and many others actually, they are mean field games. But they're not being studied as mean field games before. Because I think because we don't have tools to do it. It's a very simple game. Right? By the way, there's many different variations of congestion game. I'm talking about atomic spherical congestion game, which is a very hard case for congestion game. Right? So in this case, you have a finite number of agents. These agents need to route certain amount of traffic over the network between source and destination pair. Okay? So in this case, each agent, the decision needs to just the amount of traffic you assign to each link of the road. Okay, so that UI is a bit each of them are the amount of traffic assigned for each agent. And each agent, what they want to do is that they want to minimize the total congestion cost among all the selected paths. They want to route their traffic. Okay, so if a particular link is non-zero traffic, you need the total cost you incurred is need to time the delay function. Okay, the cost of that link, and this cost is generally dependent on the total number of traffic that are using that particular link. Okay, you can see in this form, it's a game. This cost function calculator. Okay, if you're familiar with congestion game or routing game in general, you will know that people typically worry about price of anarchy. Okay, so the efficiency loss of those things. Unfortunately, for this kind of game, although it looks very simple, the tight bound for price anarchy was only derived very recently. It's a pretty price anarchy is a challenge. Okay, but this is also mean field game. Then I can ask you a question. Can you use mean field game theory to solve this game for you? I just want to, I started asking those simple questions, but I was able to, but it's hard to see how this Hamilton, Jacobi, Fokker-Planck, those kind of standard way of describing mean field equation carry over or can be applied in even this simple setup. So in the literature, at least, there's no such discussion, right? So we feel like mean field game theory has been studied a long time, very interesting. There's a big gap between the theory and the application need, okay? So what we want is a framework that is model-wise is more general, more realistic. We could incorporate SDE, but we don't want to restrict to that. We don't want to state the principle just in terms of SDE. And we want to not only characterize the equilibrium, we want to know how to compute them. You want to further challenge yourself is that we not only compute them, but to know whether this equilibrium is good or bad. Okay, we design a game that induces a good equilibrium for perspective. We want to do this. So our main work result is the following. So we find out a class of quite important class of mean field games are equivalent to the optimization problem in general infinite dimensional, possibly infinite dimensional vector space. Okay. We were able to accomplish most of these objectives, at least to a certain extent. So that's the message. All right, let me get to some details. I don't know how much time I have, but I think I'm okay. 15 minutes, okay, okay. Okay, so we're looking for a different way to look at mean field game now, okay? So now we try to model the agent dynamics using this trajectory-wise mapping. Okay, this could be continuous time, discrete time, stochastic, or deterministic. That's fine. So if you give me a control input signal, okay, or trajectory, or noise process, this thing maps to a state trajectory. That's all I need. Okay, you need some kind of consumptions. So this state space has to lie in the Hilbert space. So you have to, for the state is Hilbert space, I can do optimization. We only only require them to be in a general arbitrary vector space. The point is that by restricting this only to general vector space, we can incorporate many different information structure of the decision. Because, for example, if open loop, that's easy, right? The control space will be just the set of all the possible control signals, right? But if you want state feedback information structure, then this one would be just all the signals that are adapted to the noise process or the state process. Okay, that's also a vector space. Okay, that's also satisfies this condition. All right. And of course, the particular structure of the cost function looks very restrictive, but actually it's quite general. So this cost function only depend on some term, depend on only local trajectory. Okay, local state and control. And also depend on some mean field coupling, which is the ensemble mean of them. It's not the whole empirical distribution, but it's just a mean. This has to be the case in this case. We think we can generalize it, but let's stay with it. and also potential other term that depend on the mean. Okay, that's the particular structure of it. Of course, there's some other kind of regular condition we ensure that don't worry about them for now. Okay, surprisingly, this kind of form incorporate or include many existing existing mean field games that exist. Okay, I will just give you 2 examples to let you see. For example, the more recent work, Grammatical and Allegro School, basically they have done quite a bit in mean field games. Very recent work. They studied the so-called deterministic discrete time linear quadratic mean field games. And if you look at this, it's just these are the setup. Okay, each individual agent needs to minimize the quadratic cost subject to linear constraint dynamical system. And we can easily transform this into this form. Right? Just vectorize all this state over different times. They're doing finite time as well. And using standard Euclidean norm, we can transform into this form. Okay. We can also, the mean field game, that's the original paper, pioneer paper in Mixing Control Society, is Huang, Kane, and Mahane. And their work is they focus on stochastic, I don't know why it is missing, SDE. Hold on. Sorry, I think that's missing. Let me go back. Okay, that's fine. It's focused on this scalar stochastic differential equation. Okay. In this case, this X will be the strong solution of the SDE, right? And this will be the Brownian motion. And in this particular SDE, we can even find the explicit form of this Fi. That's not required in general. And by introducing this inner product in the signal space, we can also transform this Huang's work stochastic continuous time SDE-based mean field game formulation into this vector space formulation. So what we like is that this is more neat or compact and also easy to deal with. Okay, actually we can do many. The PV case and also this the congestion game case immediately fall into this category. Okay, so by focusing on this, we consider all of these together. Right. So that's the formulation. By the way, this part we can drop it without affecting anything. So for simplifying this discussion, I will drop it. So let's study now. From now on, I will study this game. Okay. So in addition to a vector space formulation of the game, another thing we did is that we directly considered finite population. We didn't go to infinite and come back. We didn't study continuum model. Okay, this is a particular case. Our particular problem enable us to do this. Okay, so this avoid many technical complications. Right. So in this case, we can easily derive mean field equations. I don't want to go into details. Roughly the same idea. Given the mean field coupling term, you hold this fixed, this lambda fixed, and this will be your best response. And given the best response, control response, the state response, this lambda should generate the same mean field term. Okay, the same principle, but we just do derive this one based on this general formulation. What we can show is that any solution to these mean field equations is epsilon s, and epsilon goes to 0 as n go to infinity. This requires some proof, but it's not surprising. It's pretty good because the reason is that we're doing this for this unified model so that you don't need to derive the same principle under different specifics. Okay, that's one thing that's good. Another thing that's good is, most important is that this one now allow us to see something that is hard to see in the SDE-based model. I'm not sure how this looks to you. Basically, you have the I from 1 to n, by the way. It's many of them. Right, and you have one thing here. This looks a lot like the optimality condition of some constraint optimization problem. Okay, so that brings us to a main result of our work, is that any mean field game, you can formulate in this form, any of them, that as long as you can write in this form in vector space, is associated with a social welfare optimization problem. Okay, and this is n-player mean field games will become equivalent to a social welfare optimization problem among n+1 agents. You have to specially construct this social welfare optimization function. Okay, and whenever this optimization problem is convex, then the solution of this mean field equation will coincide with the solution of this optimization problem. Okay, that's the result. It's very easy to check if you find out this relation. So you can check the optimality condition that will give you when it's a convex, it will give you exactly the mean field equation you have. That's basically the idea of proof. Okay, so why this is useful? Well, it's really connect mean field game with optimizations. First of all, it tells you can now compare different mean field games equilibrium. Okay, because you know they are optimizing the corresponding optimization problem. You can compare them whether one is good or bad. Okay, that's one thing we like. Second is that if you're social planar, if your objective can be captured by this welfare optimization problem, now you know you can design mean field game whose emerging epsilon Nash equilibrium achieves the social objective. That's another thing that's from the other side. And more interesting, I feel like, is that now solving the mean field game become a convex optimization problem. That's the part we like. That's we need to compute them, right? So if you work in this mean field game, you will see that there's no general theory for computing the mean field equilibrium. But once you do this application, specific application, they propose specific ways. But roughly, most of them do the same thing, okay? If you gave me the mean field term, I generate the best response for each agent, and then the best response should eventually, and then given the best response, I update the mean field term, and this looping eventually, hopefully, can converge. And in general, there's no convergence guarantees. And João Ligaro's their work, whole paper is about different ways to characterize how under what condition this loop will converge. Okay, under a particular special linear quadratic mean field game case. Right? What we find out that you don't need to design specialized algorithm to compute mean field equilibrium now. Okay, we study this equilibrium. We can just work at the corresponding optimization problem. And one good feature about this optimization problem is that it's dual decomposable. Okay, and we realized that many existing results in the mean field literature is just prime dual update of this dual form of our social welfare optimization problem. Okay, in that sense, we don't really need to develop specialized theory to prove convergence or computing. We can just use off-the-shelf convex optimization algorithm with guaranteed performance, right? We try this for the same example that their paper using, the same charging example. Instead of directly try to use their approach to compute this, we transform into optimization problem, the corresponding one, construct specially, and we use just ADMM. This is our result, converts much faster than their work. Okay, and we don't need to develop specialized theory for convergence analysis. Okay, so that's the, we feel like this is quite useful, at least for this simple finite time, discrete time case, right? So also, okay, now, because our result is in the unified model, so we can directly use it to answer the question I just asked, this atomic congestion game. I can use our approach to compute the epsilon Nash equilibrium for this game as well, if you're interested in that. Okay, so a big hurdle is that, I mean, now the big limitation now sounds like is the result is that if this optimization is convex, then they are equivalent. Now the question will be, can we generalize it? Well, not too much. So you need to look at the property of the two problems now. Okay, so what we really care about, if you really think about them, is the following: the mean field equilibrium uniqueness, existence, or whether it's social optimal or not. Okay, you don't get, if you have strictly convexity of this problem, you get all of these properties. Okay, but if you don't have it, we show that at most you need, at least you need strong duality. Okay, that's the key thing. So as long as this problem has strong duality, it doesn't need to be convex, then this many other properties hold. Okay, not completely. So for example, if strong duality and this mean field coupling term is monotone, that's a quite common assumption made in literature. Then strong duality if and only if mean field equilibrium exists. Okay, we have sufficient natural conditions. This actually generalize some result in the literature, at least for this particular class of mean field games. if you look at literature, typically if you want to solve existence of mean-field equilibrium, they will need this one to be monotone. That's first of all. Second, they need individual cost function to be convex. And they only have sufficient condition for that, for existence. And we have sufficient natural condition if you look at from the optimization perspective. Okay. So I feel like this is a very nice way to look at mean-field game from optimization perspective. So with the next few minutes, I may briefly comment. I'm not sure if you work on games, this may remind you a lot, or this looks similar to the connection between Nash equilibrium and optimal solution of some potential function optimization problem, right? It looks like potential game. Okay, the question is that whether this is just because it's a potential game. The answer is no. Okay, so how does it relate to potential game in general? Okay, so well, I would say sometimes this problem is indeed a potential game. Okay, for example, in scalar deterministic case, I can have an if unknown if condition for this problem to be potential game by some famous result. And but you need to satisfy some special conditions. And I would say in general, this game is not potential game. But the more important point I was trying to make is that whether this game is a potential game or not has nothing to do with the importance of this link, this connection. Okay, let's just look at the case. So suppose this game is a potential game. Let's look at it as I promised. Look at this intersection point. Suppose this is a potential game and a mean-field game, satisfy our conditions. So what does this mean? How should we approach this problem? Well, we can approach from potential game and our approach mean-field game. They are giving just different things. Okay? For example, potential game, you have potential function. In this case, will be different from the modified social welfare optimization problem, the optimization function we are optimizing. Okay, they are different. So some people may question whether this is just a potential function. The answer is no. Okay, and also secondly, the optimizer of the potential game or potential function will give you Nash. All right, the optimizer of the social welfare function will give you only epsilon Nash. In that sense, this is a stronger case. Okay, if this is epsilon Nash, that's the difference. All right. Secondly, function batch response converge to Nash, but this complexity grow exponentially as the number of agents increase. Okay, some people discuss how to reduce the complexity, but in general it's not possible, right? But in this case, because this mean-field game is fully parallel, once you have, because it's dual decomposable, so it can be fully parallel for each agent. Okay, especially the primal update given the dual is completely decentralized. So this is very scalable. And communication-wise, this guy is more demanding, and this one is almost decentralized. I would say hierarchical decentralized. Okay, so there are trade-offs, right? So if you're satisfied with Nash equilibrium, epsilon Nash, then you have a lot of benefit. Okay, if you don't, you have to use this, take the hard way, right? The question is that if you're interested in this, then our connection is very useful for you to solve the mean-field equilibrium. So that's the point.